Now we have talked about forced harmonic vibration a lot, but what is the source of the forcing in most of the machinery? So source of forcing on most of the rotating machinery is the eccentric rotating mass. This is the most common source of forcing in machineries due to which the force vibration occurs. And we will just see this case because this one specific case which will help to find out the loading. So if the center of mass of the body, the rotating mass, is at the distance e from the geometric center, like the center of mass is at a distance e from the geometric center, then the centrifugal force due to this mass will be equal to m e omega square. The centrifugal force is mr omega square. So the force will be equal to m e omega square. And if the machinery, in this rotating component is inside a machinery which is supported on a base with a damper and a spring system, then the force transmitted to the base will be the centrifugal force will be F is equal to m e omega square. So the force transmitted to the base will be projection of this force in the vertical direction. So that will be equal to F will be equal to m e omega square sine omega t. So this is something similar to the forcing function that we consider in the case of forced damped vibration. So in that case, the f sine omega t was the function, forcing function. So the forcing is this much. So F is equal to m e omega square in the case of rotating unbalance. So this is one particular case of interest. For formula is simple. Rest all definitions about omega, damping ratio, spring constant, natural resonance, natural frequency, the resonance, transmissibility, all of the conditions apply. Just the forcing function is now also a function of omega. That's the only difference. Because of this that difference, since the forcing is also now function of omega square, will you get your displacement that was equal to F divided by k minus m omega square whole square plus c omega whole square here c omega whole square. So F is now equal to m e omega square. So x will be equal to m e omega square k minus m omega square divided the whole square plus c omega whole square, and the space tan z is equal to c omega by k minus m omega square. That remains same, that doesn't change. So only the forcing changes, so the displacement changes. So now the resonance condition that is determined by the displacement amplitude from derivation, this one, it will change. The resonance condition changes. So the value at which the resonance occurs for the rotating shaft, the angular frequency for that is omega, and that is omega r. This is called critical speed of the shaft. So for a given machinery, for a given damping and spring attached to the machinery, you have the rotating components, and when the rotating components rotate at a particular critical speed, resonance occurs, and when the resonance occurs, that speed is called the critical speed of the shaft, and it has to be avoided to prevent the resonance. Now, if you remember your earlier expression for the magnification factor from which you determine the conditions of the resonance, it was equal to 1 by square root of omega by omega n whole square, then again square, plus 4g square omega by omega n whole square. So this expression we use to get the resonance by equating this denominator is equal to 0. Now in the present case you will get an extra omega by omega n square in the denominator if you non-dimensionalize the equation. So here also the same condition will apply. You will make denominator equal to 0 and you will get resonance omega r equal to omega n 1 minus 2 g square. So same condition for the critical speed. Nothing much will change. And the resonance will remain same, and when the resonance occurs, that time the rotating speed of the shaft is called the critical speed of the shaft. The critical speed of shaft is equal to n, to 2 pi by omega r. Now we will take some numerical example from the topic of force damped oscillation numericals. So we take first numerical. Here it is given that there is a rotor of weight 100 Newton, and that is mounted midway on 20 dia shaft and supported by two bearings. So bearings are 800 apart bearings. So due to manufacturing defect, the center of gravity of rotor shaft is 0.01 very small value, you can see, away from geometric center. So just 0.01 difference in the position. So this is a case of rotating vibrating load, geometric center. So then due to that the forcing will occur, force vibration will occur. So we are asked to determine the amplitude of steady state oscillation, amplitude steady, and dynamic load on bearing when shaft rotates at. So here you will get an idea of critical speed in this example. The shaft rotates at 3000 rpm. Now and it is said that assume E, the modulus of elasticity, is equal to 2 into 10 to the power 5 Newton per millimeter square. So here the problem is given to us only to find the elasticity of the system. There is the shaft, rotor shaft, which is supported on two bearings 800 away, and the mass of the rotor is given as 100 Newton, and the elasticity is given as 2 10 to the power 5. So we have to determine K for ourselves and mass for ourselves. We'll go about solving this problem. So for calculating the stiffness of the system, we'll use the theory of materials formula. The stiffness, we know that it is given by weight by displacement. In the spring mass system, you have a static displacement delta and you have a weight W. So K is weight by W, weight by delta, the static deflection. So if you can calculate the static deflection of the rotor and you know the weight of the rotor, by that you can get the stiffness of the rotor. So static deflection of the rotor from our theory of material, strength of materials, strength of materials, we know that the deflection of a shaft supporting between two bearings is omega is W L cube by 48 pi. So if you substitute the value 100, length is 0.8 meter, and so the length is 800 mm, so 0.8 meter, and 48 2 into 10 to the power 5 Newton per mm square, so 10 to the power 6 here, and I of the shaft that you have to calculate for the rotating, for the cylindrical body, it is 5 by 64 d square, d is 20, it is given, so 0.02 in SI units, power 4, this is I for the shaft. So this value calculate, finally you will get static deflection is equal to 0.679 mm. Now stiffness K is equal to 100 Newton divided by 0.679 mm. So for that you will get stiffness is equal to 147.27 Newton per meter. Now from stiffness of the shaft you can calculate the natural frequency of the shaft, that will be equal to K by M, the mass of the shaft. So K is 142.27 and mass is weight by G, weight is 100 Newton, G is 9.81. So the omega N will be equal to 122.2 radian per second. So this is the natural frequency of the shaft due to the static deflection. Now that was the natural frequency. Omega natural is equal to 120.2 radian per second. What is the actual frequency omega of the rotating of the shaft? That is 2 pi into n, RPM is given 3000 by 60. This will come around 314.16 radian per second. So the real frequency is higher than the natural frequency. So you have in the graph you have a omega by omega n greater than 1. So this portion somewhere you will lie in the graph of the magnification factor. So what are the amplitude of steady state vibration that you saw? The amplitude is x, given by f divided by square root of k minus m omega square whole square plus c omega whole square. Now in the present case we are not given with any damping, so c is equal to 0, and the forcing function is m e omega square that we just saw for the shaft with a eccentricity e. So you substitute this value here, you will get the deflection for this condition. Given condition is m e omega square divided by k minus m omega square whole square. So the root and omega square and the square will get cancelled out. We will get m e omega square divided by k minus m omega square. If you take e outside, you will get, yes, so if you take m outside in the denominator and cancel it from the top, you get e omega square divided by k by m. K by m is omega n square, natural frequency square, divided by omega square. So this is the deflection of the shaft under eccentric loading for a given angular velocity. We will substitute our values here. We know the eccentricity, that is given as 0.01 mm, so 10 to the power minus 3. And the omega speed, angular speed of rotation, the real speed of rotation 314.16 whole square divided by omega n. Omega n is 120.2 roughly whole square minus omega again 314.16 whole square. If you evaluate this value, you will get an answer of from 0.0117 mm. So if you don't consider this scaling factor for meter here, so again you have to convert. So this is the static, this is the maximum deflection for the given condition. The formula for the deflection for eccentric loading is given here, and you can remember it. For eccentric loading, the deflection is equal to eccentricity of the shaft, and omega square you can take the common from denominator and from numerator, where omega n by omega whole square minus 1. So we have done the derivation also. Here you can remember this formula simply. Now we come to the second part of the problem. It was asked to find the dynamic load transmitted. So this is the answer for the first part. Second part is dynamic load transmitted to the base. So the dynamic load, here we have the shaft and we want dynamic load at the bearings. Dynamic load at bearings. So this shaft is having no damping. Whatever load thrust at the bearing you will get will be the flexibility of the flexing of the shaft. So you know the the displacement of the shaft, the dynamic displacement, and if you multiply the k with the displacement, the stiffness of the shaft with the displacement. So the stiffness that we are talking about here is the bending stiffness. So then you can get the forces at the bearings. So bearing force will be equal to the force due to flexing of the shaft, that is the stiffness, bending stiffness multiplied by displacement, that is equal to 0.0117 that we saw in the part 1 answer, and the K was 147.27. So, and since the flexing force is in the downward direction, the bearing force will be in the upward direction because it's a reaction force. So you should use a minus sign also here, and you have minus sign for the deflection, minus 0.07, the those will get cancelled out. Final answer for the bearing force you get as 1.723 Newton. So this much thrust is accepted as each bearing. Total load at each bearing will be equal to weight plus dynamic load. Dynamic load will be varying sinusoidally. So this is the answer for the second part, the dynamic load. We'll take another example in the topic of forced oscillation. In this case, a machine is given with 100 kg mass, and it is supported on springs of total stiffness 700 kilonewton per meter, and it is having an unbalanced rotating element. So this is the most a common form of forcing in machinery, unbalanced rotating element, and which is the unbalanced element results in disturbing force of 350 Newton. 350 Newton, and the unbalanced rotating mass is rotating at a speed of 3000 rpm. So assuming damping factor, now in this case, in the earlier example we saw there is no damping. Here, assuming a damping factor of 0.2, we have to determine first amplitude of unbalanced motion. This force due to the unbalanced mass. So what will be the amplitude of motion? That is simply the amplitude of forced vibration. B is transmissibility, and C is transmitted force. We will go about solving this problem. Solution of this problem will use the formula that we have determined for the force vibration. First, we should determine omega n, that is the natural frequency of the system, that we can just get from k by m. So k is given here, string of stiffness 700 kilonewtons, so 700 into 10 power 3. Mass of the system, you know, 100 kg. So so you get omega n nearly 120 radian per second, and then you have the formula for x, the maximum displacement under the vibrating load, that is F by K, square root of 1 minus omega by omega n whole square plus 2z omega by omega n whole square. So F by K is nothing but xs. So it's the same formula we are using here. And what is omega? Omega, you are given a rotation speed of 3000 rpm, so 2 pi into 3000 by 60, that is equal to 314 radian per second. So this is, and the F is given here, the force due to unbalanced is 350 Newton. So we have all the quantities for determining x here. So 350 divided by k, that is equal to 700 into 10 power 3 divided by square root of. So we have non-dimensionalized the denominator because v is given. We can calculate c also, and we can do like that also. But it's an easier method. 120 by 314 whole square plus 2z, z is given as 0.2, and omega by omega n again 120 by 314, this thing whole square. If you simplify and evaluate this expression, you get x is equal to 0.0379 mm, not meter, mm. Multiply with 10 power minus 3, you will get in meter, you can get in mm. So this is the diffraction of this system. Now coming to the second part, it was asked to calculate the transmissibility of the system. For transmissibility, we have the equation that the transmissibility ratio is equal to square root of 1 plus 2z omega by omega n whole square divided by square root of the same thing that we get in the denominator for displacement, 1 by omega n square whole square plus 4z square omega by omega n whole square. So here we know most of the values, so we substitute the values for transmissibility ratio. You have 1 plus 2, z is 0.2, omega is known, omega is 314 and omega natural is 120, and this thing whole square of this thing, then you have square root of 1 minus 314 by 120 whole square, this expression whole square, plus 4 into 0.2 square, 314 by 120 whole square. If you substitute these values and calculate the answer, you will get a value of 0.137, the transmissibility ratio. And third part, they're asking us for the transmitted force. So transmitted force is nothing but the force, disturbing force multiplied by transmissibility ratio. So disturbing force, we have been provided here that the disturbing force is 250 Newton. In the problem itself it was given, and transmissibility ratio is 0.137, so 47.89. So you can see here that the actual disturbance in the machinery was 350 Newton, and it was reduced to this value before transmitting to the structure. This is the principle of vibration isolation. So now ending the chapter, we'll move on to see some gate question, how the gate question can be formed from the chapter of vibrations. So we'll take the first question that was asked in GATE 2011 recently. It is given that a mass of 1 kg is attached to two identical springs, each with stiffness K is equal to 20 kilonewton per meter. So it is shown as the figure is given like this: two springs supporting a mass, and the mass is having wheels on the ground, and the mass is 1 kg. The stiffness of each spring is 20 kilonewton per meter, and under the frictionless condition. So there is no friction from the ground, so there is no damping of the oscillation. Then what is the natural frequency? So that is the question asked. So it is very simple. The natural frequency is equal to solution. Natural frequency is equal to angular natural frequency is equal to k root over k by n. But for that you have to find the equivalent stiffness. So how do you determine the equivalent stiffness of springs connected in parallel? You have mass m, you have displacement delta. So here the mass, effective mass will be m by 2. So you have k is equal to weight by deflection delta. Deflection will be same for both the springs because they are connected in parallel, but the weight will be divided by 2. So here you will have, so you let's say if you have W in this one, you will have W in this one. So the net formula will be equal to k by W by 2 delta. For the same deflection, you will have force W1 equal to K delta and W2 equal to K delta, K1 delta, K2 delta, and hence the net force, if you do a summation, W1 plus W2 equal to K1 plus K2 delta, and hence the springs are just added because this is the net force, this is net deflection, so spring constant is just added. So here we have 20 kilonewton per meter. Finding the natural frequency will be 20 plus 20, you have the effective stiffness 2 into 20 kilonewton per meter, so 10 power 3, and the mass is given as 1 kg here. So this you can see the square root expression is 4 into 10 power 4, this is 2 into 10 power 2, if you use square root, so 200 radian per second. And what is the frequency? It is 1 pi 2 pi of omega, so 200 by 2 pi, that is 100 by pi. So this is one of the options. It is roughly around 32 hertz. This is the correct answer. Now we will take another gate examination. Here again a similar expression, a similar system is given, but this time this is a forced oscillation problem. So here again a mass is attached to a spring, the cart is there, which is having wheels, and the spring spring is there, the mass m is attached, and there is a harmonic force in this case. This question was asked in GATE 2010. So the harmonic force is equal to 100 cos 100 t. Omega is given 100 and the amplitude of force is also 100. And the stiffness of the spring K is given as 3000 Newton per meter. And mass is m. So if amplitude of motion is 50 mm, then what should be the mass? This is a question asked. So we will go about solving this problem. For that, we will remember our basic formula for the force oscillation, that F is equal to F by K and the square root of the damping is 0 in this case. So you have 1 minus omega by omega n square whole square. So in this case, and then you have 2 z and then omega by omega n, but z is equal to 0. There is no damping. So that term will neglect. You have to be fast in these things. So this is the function. If you simplify this thing, you will get x into 1 minus omega by omega n whole square is equal to f by k. Omega natural is given by k by n, square root of k by n. So if you just multiply on rearranging, you will get k minus omega square m is equal to f by x after some rearrangement, simple rearrangement. So now in this case, k is given as 3000 and omega is given as 100 because the forcing function is 100 cos 100 t. So from that we get omega is 100. The mass of the system that we have to determine, and the forcing is amplitude is 100, and the displacement has to be limited to 50 mm. So 50 mm is 50 into 10 power minus 3. So on solving this equation for m, you get m is equal to 0.1. So this is one of the answers that you can choose. We'll take another GATE examination question that was asked in year 2009. So here it is given that the vehicle suspension system is there, vehicle suspension system, and it is having a spring and a damper, obviously. So the stiffness of spring is equal to 3.6 kilo Newton per meter, and the damping constant of the damper vibration isolation system is 400 Newton second per meter. So the stiffness and damping constant are provided. Damping is 4000 Newton second per meter, and if mass is 50 kg of the system, if mass is equal to 50 kg, then you calculate the damping factor. Damping factor is nothing but z, and calculate the frequency of damped oscillation. Frequency of pre-damped oscillation. So we'll go about solving this problem solution. So z, we know that it can be we can get by c by c critical damping. So the damping constant is given as 4000 in SI units. Critical damping is 2 square root of k by m. K in this case is given as 3600 because kilometers, 1000 divided by 1000, and mass is given as 50. So if you simplify this expression, you get a value of 0.741. So that is one of the expression with the answer. This is the case for underdamped. Now for the second part, we are asked for damped oscillation frequency. So damped oscillation frequency omega d, as you remember, is given by omega square root of 1 by t square. For that you have to calculate omega first. Omega you have to calculate by square root of k by m. that if you substitute the value, it will be square root of 3600 by 50. This will come roughly near 8.48 radian per second. And then you have the value of G. G is what we have just determined, equal to 741. 0.741. So we substitute the value for omega d, we get 8.48 multiplied by 1 minus 0.741 whole square. This is coming roughly near 7.48 radian per second, but in the options the speed is given in RPM. So we calculate RPM as omega d by 2 pi. That will be equal to 7.48 divided by 2 into 3.14. Comes around nearly 1.19 hertz. So this is also one of the answers that you can pick up from the option. Now we'll take one more example from GATE. This question was asked in GATE 2006. So here the problem given is that a machine is there and the machine is having 250 kg mass. It is supported on springs and the stiffness of the spring is 100 kilonewton per meter, total stiffness, the combined equivalent stiffness, and machine has a unbalanced rotating mass, and that unbalanced rotating force, in this case the radial force is given. So unbalanced rotating force is 350 Newton at 3600 RPM. This is a speed of rotation of the unrotating balance in the unbalanced rotating element in the machine. So assume damping factor of 0.15, G is equal to 0.5. So what is the value of transmissibility ratio? So transmissibility ratio, we solve this problem. We know that the expression, let's write the formula here. However, if you remember the formula for undamped case, it will be much simpler. So transmissibility ratio is equal to 1 plus 2g omega by omega n whole square divided by 1 minus omega by omega n whole square, and the square, total square of that, plus 2g square omega by omega n whole square. But now in this case there is no damping. So no damping. So actually there is damping in this case 0.15, but the value is very small. So you can see that v was much smaller than 1. So what we will do here, that it is very complicated to find out the solution for the actual expression here. You can see it's quite complicated. So we calculate the value of transmissibility ratio for undamped case, and then we will try to see that if one of our option is close to that. So for transmissibility ratio for undamped case, we will get z equal to 0. If you see this becomes 0, this becomes 0, and you will get basically transmissibility ratio is equal to 1 divided by 1 minus omega by omega n whole square. So this is omega n square divided by omega n square minus omega square. For that we have to calculate omega, that is natural frequency, omega n is equal to k by m. So k is given in this case as 100 kilonewton per meter, 10^3. Mass is given as 250 kg. If you get this expression, it's around 20 radian per second, and the real for angular velocity is 3600 RPM. So 2 into pi into 3600 by 60, this will come nearly 377, and the transmissibility ratio is the undamped transmissibility ratio is omega n square by omega minus omega n square, So this is equal to 20 square by 377 square minus 20 square. So the value will come around 0.0028. So to see the option that those are given as 0.053, 0.99, the C is given as 0.016, and D is given as 0.0028. So in that range 0.00, none of the options are there. So from that case also we can determine that the correct option is D. And like it will come somewhere now 0.0030, so the correct option is 1.0028 for G is equal to 0.5. So like that you have to be a little bit smart in solving the problem. If G is very small, you can take the formula for undamped case, and it is